Here's a question that will sound a little morbid, but stay with me. When you die, where do you go? Now, I don't mean heaven or hell or any of that. I'm a physicist, and I'm asking you something much more interesting. Where does the stuff that is you actually go? Because here's what's strange. You've got about 7 billion atoms in your body right now. That's a 7 followed by 27 zeros, 7 octillion atoms. And when you die, not one of those atoms disappears, not a single one. They're all still here. So, if nothing is lost, in what sense are you gone? That's what we're going to figure out today. By the end of this, you'll understand something profound about what you're made of, where it came from, where it's going, and why the very idea of you is stranger than you ever imagined. I think you'll never look at yourself, or a blade of grass, or a distant star, or even a breath of air, quite the same way again. Let's start with something simple. Let's start with a candle. You light a candle, and it burns. The wax melts, the wick glows, and after a while, the candle is gone. Now, you might say the candle has been destroyed, but that's not quite right, is it? Where did the candle go? Well, some of it turned into light. Photons bounced around the room and eventually got absorbed by the walls, warming them slightly. Some of it turned into heat, which warmed the air and spread out through the room. And some of it, the carbon in the wax, combined with oxygen in the air to make carbon dioxide. That carbon dioxide is now floating around, maybe drifting out the window, maybe being breathed in by someone walking by outside. The point is, the candle didn't vanish, it transformed. The atoms that made up the candle are all still somewhere. They've just rearranged themselves into different configurations, different molecules, different forms. This is one of the most fundamental laws in all of physics. Energy cannot be created or destroyed. It can only change from one form to another. We call this the first law of thermodynamics. And I want you to understand this isn't just a good approximation. This isn't just usually true. In every experiment ever conducted, in every observation ever made, this law has held. It is as close to an absolute truth as we have ever found in physics. Now, here's where it gets interesting. You sitting there listening to me, you are not so different from that candle. You are in the most literal sense burning right now. As you sit there, your body is taking in oxygen, combining it with the food you ate and releasing energy. But let me tell you exactly how much energy, because the numbers are extraordinary. At any given moment, your body contains about 250 grams of a molecule called ATP, adenosine triphosphate. That's the energy currency of life. Every cell in your body uses ATP to do work, to move, to build proteins, to think. And here's what's remarkable. That 250 gram of ATP represents only about 4 watts of power. The equivalent of a small LED light bulb. That's all the ATP you have at any moment. But wait, your body uses far more than 4 watts. At rest, you're burning about 80 to 100 watts. When you're exercising, maybe 500 watts or more. So how does that work? The answer is that your cells are recycling ATP at a furious rate. Each ATP molecule gets used and regenerated about 1,000 times per day. Your body produces, uses, and regenerates roughly your entire body weight in ATP every single day. 40 to 70 kilograms of ATP made fresh every 24 hours. Let me put this another way. Over the course of a day, a healthy person produces about 1/200 watts of total energy. That's enough to power 1/200 household light bulbs simultaneously. If you could somehow harness it all at once, of course you can't. The energy is released gradually, continuously, as your cells burn through that recycled ATP. And where does this happen? In tiny structures inside your cells called mitochondria. You have about 10 million billion of them, 10 quadrillion mitochondria, each one a microscopic power plant, each one burning fuel and churning out ATP. The mitochondria have their own DNA separate from the DNA in your cell's nucleus. This is because they used to be free-living bacteria. About 2 billion years ago, one of our single-celled ancestors engulfed a bacterium but didn't digest it. Instead, they formed a partnership. The bacterium provided energy, and the host cell provided protection and nutrients. Over billions of years, that bacterium became the mitochondrion. You are, in a very real sense, a colony of organisms. Here's another way to think about the energy numbers. The average cell uses about 10 billion ATP molecules per day. You have roughly 37 trillion cells. Do the math, and your body is cycling through something like 3 to 10, the 25th ATP molecules every day. That's 300 trillion molecules being built, used, and rebuilt in a continuous chemical symphony that never stops from the moment you're born until the moment you die. And consider this, your brain, which is only about 2% of your body weight, uses about 20% of your energy. A single thought, a single memory being formed requires billions of ATP molecules. When you're thinking hard, solving a problem, your neurons are firing at tremendous rates, each firing requiring billions of sodium ions to be pumped back across cell membranes, each pump cycle requiring ATP. It's estimated that a single action potential, one electrical signal traveling down one neuron, requires about 1 billion sodium ions to be moved, which means about 1 billion ATP molecules to reset that one neuron for its next signal. When that symphony stops, that's death. Not because the atoms go away, but because the process stops, the pattern stops being maintained. But I'm getting ahead of myself. Let me go back to basics. And just like the candle, you are constantly releasing atoms into the world. Every breath you exhale carries away carbon dioxide, about 200 milliliters of it. That's carbon that was part of your body a moment ago, now floating free. Every drop of sweat releases water and salts. Every time you shed a skin cell, that's atoms leaving your body. You lose about 30,000 to 40,000 dead skin cells every minute. Every minute. You are not a static thing. You are a process, a river of atoms flowing through a particular pattern we call you. Now suppose you wanted a physicist to speak at your funeral. I've actually thought about this. You'd want the physicist to talk to your grieving family about the conservation of energy. You'd want them to understand that your energy has not died. Here's what I'd want that physicist to say. No energy gets created in the universe and none is destroyed. All your energy, every vibration, every bit of heat, every wave of every particle that was your beloved, it all remains in this world. The photons that bounced off your face, the particles whose paths were interrupted by your smile, by the touch of your hair, hundreds of trillions of them, they've scattered off into the world like children running in all directions. They're still out there. They will always be out there. According to the law of conservation of energy, not a bit of you is gone. You're just less orderly. That's all. But wait, let's go deeper, much deeper. Let's ask where those atoms came from in the first place. Pick up your hand and look at it. Let me tell you exactly what you're made of. By mass, you are about 65% oxygen. Surprised? Most people are, but remember, you're mostly water, and water is H2O, and oxygen is the heavy part. One oxygen atom weighs 16 times as much as one hydrogen atom. So even though hydrogen atoms outnumber oxygen atoms 2 to 1 in water, oxygen dominates by weight. After oxygen comes carbon, about 18% of your mass, then hydrogen at about 10%. Then nitrogen at about 3%. Together, these four elements, oxygen, carbon, hydrogen, and nitrogen, make up about 96% of your body mass. Just 4 elements out of the 92 naturally occurring ones. The remaining 4% includes calcium, about 2%, mostly in your bones and teeth, phosphorus, about 1%, critical for your DNA and ATP. Then smaller amounts of potassium, sulfur, sodium, chlorine, and magnesium. And finally, trace elements, iron, zinc, copper, iodine, and a few others in tiny amounts, but absolutely essential. The iron in your body, if you extract it at all, would make a nail about 3 in long. That's it. But without that tiny bit of iron, you couldn't carry oxygen in your blood, and you'd die in minutes. Now, let's count atoms instead of weighing them. By number of atoms, you're about 63% hydrogen, 24% oxygen, and 12% carbon. The vast majority of atoms in your body are hydrogen. The simplest atom, just 1 proton and 1 electron. Here's a striking way to think about it. There are more atoms in your body than there are stars in the observable universe. The observable universe contains roughly 200 billion galaxies, each with roughly 200 billion stars. That's about 4 and 10^22 power stars. But you have 7 twalons 10^27 atoms. You contain about 100,000 times more atoms than the universe has stars. Now I want you to consider the carbon atoms in your skin. There are about 700 billion of them in your body. 7. 10. The 26th power. Where did they come from? Well, you ate them. They were in your food, maybe in a piece of bread or a carrot or a steak. And where did the bread get its carbon? From the wheat plant, which pulled carbon dioxide out of the air during photosynthesis. And where did that carbon dioxide come from? Other plants and animals that breathed it out or decomposed or burned. But trace it back far enough and you get to a remarkable place. The carbon in your hand was not always on Earth. Wasn't even made on Earth. It was forged in the heart of a dying star. Let me explain this carefully because it's one of the most beautiful things we've discovered about the universe. In the beginning, just after the Big Bang about 14 billion years ago, the universe had only the simplest atoms. Let me be precise about this because the details matter and they're fascinating. At the very beginning, in the first fraction of a second, there weren't even atoms. The universe was a soup of quarks and gluons, so hot and dense that nothing we would recognize as matter could exist. The temperature was over 1 trillion degrees. As the universe expanded and cooled, quarks combined into protons and neutrons. This happened when the universe was about 1 microcond old. Think about that. 1/1,000,000th of a second after the Big Bang, the building blocks of all matter came into existence. But even then, it was too hot for protons and neutrons to stick together. They would combine and immediately be blasted apart by the intense radiation. It was like trying to build a house of cards in a hurricane. In the first 3 minutes after the Big Bang, the universe was a rowing soup of particles at unimaginable temperatures, about 10 billion degrees. At 1 second old, it was still too hot for even simple atomic nuclei to survive. Protons and neutrons were forming and breaking apart constantly. Here's a key fact. At 1 second old, there were about 7 protons for every neutron. Why? Because neutrons are slightly heavier than protons. And in the hot conditions of the early universe, the reactions that converted neutrons to protons happened slightly faster than the reverse. This ratio would turn out to be crucial for the chemistry of the entire universe. But as the universe expanded, it cooled. And when it cooled enough, about 3 minutes after the Big Bang, something remarkable happened. Protons and neutrons began sticking together. First they made deuterium, heavy hydrogen, 1 proton and 1 neutron. Then helium-3, 2 protons and 1 neutron. Then helium-4, 2 protons and 2 neutrons, and a tiny, tiny bit of lithium-7. The timing was everything. By about 3 minutes, the temperature had dropped to about 1 billion degrees, cool enough for nuclei to form, but still hot enough for fusion to happen. This window lasted only about 17 minutes. By 20 minutes after the Big Bang, the universe had cooled too much. The density dropped. The particles were too far apart to collide often enough. And so, the cosmic nuclear reactor shut down. What was the result? A universe that was about 75% hydrogen by mass, about 25% helium, about 0.01% deuterium, and about 110 billionth lithium, and nothing else. No carbon, no oxygen, no nitrogen, no iron, no calcium, none of the heavy stuff that makes up rocks and trees and people. Here's the key point. There was a bottleneck. There's no stable nucleus with 5 nucleons or 8 nucleons. Helium-4 is very stable, but if you add 1 more proton or neutron, the resulting nucleus falls apart almost instantly. And 2 helium-4 nuclei combined would make beryllium-8, which falls apart in about 10 US 16 seconds. There was no way in those first 20 minutes of cosmic history to build anything heavier than lithium. So where did all the heavy elements come from? They had to wait for stars. The first stars formed about 200 million years after the Big Bang, when gravity pulled together the primordial hydrogen and helium into dense clouds that collapsed and ignited. These first stars were monsters 30 to 300 times the mass of our sun, burning hot and bright and fast. A star, you see, is a giant nuclear reactor. In its core, under tremendous pressure and temperature, about 15 million degrees in a star like our sun, hydrogen atoms fuse together to form helium. 4 hydrogen nuclei smash together and become 1 helium nucleus, releasing energy in the process. That's what makes the sun shine. That's the power source that has kept our star burning for 5 billion years. But in more massive stars, the story goes further. When the hydrogen runs out in the core contracts and heats up even more. If it gets hot enough, about 100 million degrees, something remarkable happens. Helium atoms start fusing into carbon. This is called the triple alpha process, and it's a delicate thing. 2 helium nuclei fuse to form beryllium-8, which is wildly unstable. It falls apart in about 10 Theos-7 seconds. That's a decimal point followed by 16 zeros and then a 1 almost instantly. But if in that tiny window a third helium nucleus comes along and collides with the beryllium-8, you get carbon-12 stable carbon, the carbon that makes up the backbone of every organic molecule in your body. Here's something remarkable about this process. The reaction rate depends on temperature to the 40th power. The 40th power. That means if you double the temperature, the reaction rate increases by about 1 trillion times. This is why the triple alpha process only happens at very high temperatures above 100 million degrees, and why it's so sensitive to conditions. It's like a finely tuned mechanism. The physicist Fred High actually predicted that this reaction must exist based purely on the observation that carbon exists in the universe. He said, in effect, if carbon exists, there must be some way to make it. There must be a resonance, an energy level in the carbon nucleus at exactly the right energy to make this reaction possible. And when experimenters looked, they found exactly the resonance he predicted at 7.65 million electron volts above the ground state. This is sometimes cited as evidence for the anthropic principle, the idea that the universe must have the properties that allow for the existence of observers like us. If this resonance didn't exist, if the energy levels were even slightly different, carbon wouldn't form efficiently in stars, and we wouldn't be here to wonder about it. Nature had to be precisely tuned for carbon to exist, and here we are made of it. Now, the story doesn't stop at carbon. In massive stars, much more massive than our sun, the fusion continues. Carbon fuses with helium to form oxygen. Oxygen fuses to form neon. Neon to magnesium, magnesium to silicon, silicon to iron. But iron is the end of the line for normal fusion. Here's why. When you fuse lighter elements together, you release energy. The products weigh slightly less than the ingredients. And that missing mass becomes energy, according to Einstein's famous equation. But iron is at the bottom of the binding energy curve. Fusing iron doesn't release energy. It absorbs it. It's like trying to roll a ball up a hill instead of down. So when a massive star builds up an iron core, something dramatic happens. The core can no longer generate energy to hold itself up against gravity. In less than a second, an iron core the size of the Earth, and with the mass of the sun, collapses into a ball of neutrons just a few kilometers across. This gravitational collapse releases an enormous amount of energy, more than 100 times what our sun will radiate over its entire 10 billion year lifetime. The outer layers of the star are blown off in a catastrophic explosion. This is a supernova, one of the most violent events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy of 100 billion stars. And in that explosion, in those brief catastrophic seconds, something magical happens. The conditions become so extreme, so hot, so dense with neutrons that elements heavier than iron can form. This is called the R process, R for rapid. Neutron capture happens so fast, millions of captures per second, that the nuclei can build up faster than radioactive decay can tear them down. Think about what's happening. You have a nuclear fire raging at temperatures exceeding 1 billion degrees. Neutrons are flying everywhere. An iron nucleus absorbs a neutron, then another, then another. In seconds, it's captured dozens of neutrons and become wildly unstable. But before it can decay, it captures more. The nuclei are racing up the periodic table, becoming gold, platinum, uranium. In 2017, astronomers detected gravitational waves from 2 neutron stars colliding, and they pointed their telescopes at the source. Extreme events in the cosmos, and then all of this material, everything the star spent millions of years building in its core, everything the supernova or neutron star collision created in seconds, it gets flung out into space at 10,000 km/s. It mixes with interstellar gas clouds, and eventually those clouds collapse under their own gravity to form new stars, new planets, new everything. Our sun is a third-generation star. The dust cloud that formed the solar system was already enriched with heavy elements from earlier supernovas.